edge weight here? 1. And there are 2 ones, so we can pick in any, we can break the tie in any order you want. So let's say I pick up this one. Okay, so we have to check once we pick up an edge, before finalizing whether it can be part of the tree edge or not, we have to make sure the 2 end vertices, in this case W and V, so the vertex labels are given outside the circle and the ones inside are the component IDs. To start with, they are the same. Now what you have to check is for the 2 end vertices W and V, the component IDs are different. We don't want to pick an edge for which the 2 end vertices are already the same component. So in this case, there are different components, W and V. So kind of they are disconnected and we are trying to put them into one component. And once you combine, put them into one component, we have to identify this component with the component ID, which is nothing but the lowest of the 2 alphabets. So you have V and W. Between V and W, the lower alphabet is V. So we can label this as both of them as V. So now we have reduced from 6 components, we had 6 components, each one is one component, to 5 components. So these 2 are in one component, I have used the same color, and then we have different, the other 4 components. So now we can pick the next edge. The next edge we'll pick is the one with the minimum weight. So this one you can pick now, and check if these 2 end vertices are in different components. So X and Y, they are in different components, so you can again put them into one component. And the component ID will be the lower of the 2 alphabets, which is X. So now we have combined these 2 into one component. The next edge we can pick would be what? 2. And you can see U and V are in different components, so you can combine them into one component. So the lower of the 2 component IDs is U. So when you combine them, you can see this is in one component and these 2 guys are in another component. So you're using this edge UV to combine them. And so which means, as I said, you pick the lower of the 2 component IDs, which is U. So you have to change the labels of these 2 component IDs to U. Okay? So now all these 3 vertices belong to one component. So when I say they are belonging to one component, they are reachable from each other also. Okay? Then we pick the next lowest minimum lower weightage. Which one is the next one? Okay. And we have several trees. So if I pick, say, I can pick any of those trees here, but let's say I pick this tree. Okay, you can pick any of them. So if I pick this, there are 2 different component IDs, so you can pick that edge. And so this is S, this is all U. The lower of S and U is S. So now I can put everything in one component. So the component IDs are just to keep track of whether the vertices are in the same component or different component. Okay. Now, let's say, just for argument, this is a 3, okay, instead of a 4. And if I want to pick that edge, do you think I can pick that edge and put that as part of the tree? Based on what I have said so far, can we pick this edge of weight 3 and put that here as part of the tree? The condition that you will check is, these are the 2 end vertices S and U, and check if they are in the same or different component. They are in the same component. So if you pick an edge with the end vertices in the same component, what will happen if you include that edge into the tree? You are going to create a cycle. You see that this is a cycle. Okay? So that's the purpose of checking whether the 2 end vertices are the same component or not. If the 2 end vertices are the same component, you should not pick that edge, because if you pick that edge, you are going to only create a cycle. Because the 2 end vertices are the same component, then these 2 vertices are reachable already through some path like this, S, W, V, U. So by adding this edge, you're going to only create a cycle. Okay, so again, what is a component? The vertices within a component are reachable from each other. So all these four vertices, S, W, U and V are reachable, and S is reachable to U through this path. And you add this edge, you're going to kind of close that path and make it a cycle. And we don't want a cycle in a tree. A tree should not have cycles. You know that, right? A tree should have only the minimum number of edges that connects all the vertices and should not have any cycle. So that's why if this was a 3, the weight you cannot take that edge. Of course, here I have given 4. So the next edge you could pick would be one of these two trees. You could pick this or you could pick this. Why? If you pick this, it's going to, these two end vertices are in components S and X. If you pick this, they are also in different components. So you can pick either one of them. So let's say I pick this one and that connects these two. So between S and X, again S is a lower component ID, so you can put those two in component ID S. So now you can see all the vertices are in one component, which means they are all reachable from each other, and those edges that we have selected are the edges that will help you to reach each from one vertex to the other vertex. So these edges form your minimum spanning tree. Okay? Yeah? So you have to just pick edges in increasing order of edge weights. And the only thing you have to check is by adding an edge whether we are creating a cycle. And we keep track of that by using the component IDs. Okay? So let's do one more example. So again, to start with, each vertex is its own component. So you have A, B, B, C, and so on. So again, you have to pick, first sort all the edge weights. Okay, so we'll see the complexity after this. But so the first step is to always sort all the edge weights. So the minimum is going to be 5. So we have to check whether you can include that edge of weight 5 in the tree. So if I pick this 5, the end components are A and D. So there are different components, so I can include that edge. So I really select that edge, and between A and D, A is the lower alphabet, so I make the other one A. Now I can pick also this 5 because there are different components. So between C and E, C is the lower alphabet, so I can put them in one component. So you can see the number of components in the graph reduces each iteration. To start with, each vertex is in one component, so you had like 7 components, then you have like 6 components, you see the colors, and then you have only 5 components and so on. So eventually you want everything in one component. Okay? And so the next lowest edge weight is 6. And you check whether the two end vertices are different components. Are they different component? Right? Right. So A and F, so you can put them in one component. Again, between A and F, A is the lower one. So I have to change this to an A. So you can correspondingly change the color if you want. So now, which is the next edge you will pick?
7.
So you could pick this 7 or this 7, either way it's fine because these two are different components and these two are different components too. So you could pick one of them. So I pick the AB and make this in component A. Then you could also pick this 7 because they're still in different components. So now it is A. So now you have, which one you can pick? 5. 5? All the 5s have been picked. This 5. This 5, you're working with 7, so this 5 is already there.
No, 7.
This 7, this 5. See, these are the 3 edges.
It's going to change. It's going to change to an 8, please.
Which is going to change an A?
That last 7 coming, it's
From
A
A
to
to
E.
E.
You're going to change the, after,
The
go back
E
over. We're still on that one. See, you got the,
I picked this edge. So it was B before.
yeah, you changed it to A.
Yeah.
Then you take the next 7, right, that goes down to E.
We're going to change that one
And
to
then that'll change
It's
to
going to be a
A2.
Yeah, I changed this to an A.
Yeah, then still back on iteration 4, so he's taking the steps to get to the 5.
Oh,
Yeah, when you change.
this 5 is already taken.
You meant to say 8. It wasn't.
I'm all good with you, Tracy.
No,
This
he
is-
meant to say 8 to get to C over there.
Hmm?
He said 5, but he meant to say 8.
You
for the
mean,
next.
this is 8. This is 8. The planning from there, this is 8.
It is glare.
Why don't you move this way?
It's not gonna help.
It's the
There's big windows.
window.
Broke, no?
Well,
Broke?
I can get up there and pull it down.
Loretta is.
You already know, if you get hurt, Jack, stay won't pay for that.
I got insurance.
You may have to move somewhere in this way. Good enough now? Alright, so this is 8. So these are the blue ones are the 3 edges. Okay? So you can see now the only thing that you have to really bring into all this, because all these things are in one component, IDA. So this is the only vertex that is in one component. So you have to somehow bring this G to the rest of the components, which means even though you have all those 8s here, you can consider those 8, but if you want to pick this 8, it's going to be both the end vertices are the same component, A. So by including an 8, you're going to create only a cycle. Right? And if you include this 8, it's going to only create a cycle between these 3 vertices or this vertices and so on. So even this 9 is going to create a cycle. Okay? So the only 2 candidates are the edges connected to this G. So you have to bring this G to this tree. So you could try this one, the lower weightage. It's not going to create a cycle because they are in different components. So you can use this H weight 9 and bring that vertex into the rest of the component, which is A. So now all the vertices are in one single component. Okay? So, yes.
So, iteration 4, when we went from A to B, and then from A to C, the reason why we changed C to A is because we,
In each iteration, you take only one edge. So this edge was not chosen before this iteration. So this was a B here.
okay,
So we had to choose 7. So we preferred this one over this. So we chose this edge and made this A.
okay,
In the next iteration, we picked this 7.
okay.
We made this C and A.
So because those two were already connected, both of them kind of,
Which 2 are already connected? Yeah, these 2 are already connected. These 2 are in component C.
so because, right, okay,
And these were in one component.
alright.
Okay, so we try to connect these 2 components with that H7. Okay. Now you can also notice that in this case, these are in one component A and these are in one component C. So you can see there's a kind of a cut. A cut means these edges, right? What edges? This edge of 8A, this one of 8.7, this one 15, and this 8. These 4 edges, so not these 2 edges. These 4 edges kind of connect the vertices, or at least one vertex in this component to another vertex in this component, right? So we are picking what? Between this 4 edges, we are picking what? The minimum weight edge, which happens to be the same thing 7, right? You see that? So this is a property that's very characteristic of minimum spanning trees. And we are later going to see some proofs based on this. Okay? So basically you have two components of vertices and you have edges connecting those two components. Right? This edge does not connect to component C because this is connecting to something else, G. So these are the four edges that connect these two components. And what we are picking is the minimum weight edge between these two components. And that's what you can notice you are doing in each iteration. Okay, so even in the last one, when we pick this 9, right, the reason is this all these rest 6 vertices are in component A and this vertex is in component G. And these are the two edges that connect the two components. What are the two edges? This one and this. The vertices are in their own component. This G is in own component and these are the other vertices. So the whole thing, component A connected to component G, these are the two edges that connect the two components. And we are picking the minimum weight edge between those two edges. Okay? So that's a very important property that we use in proving things. Notice everywhere, wherever it is, we are connecting things using D. So this is one component, this is another component. Of course, there's only one edge, right? So remember this property. Okay? So every time you pick the minimum weight edge among the edges that connect the two components. Now, even in the previous example I have this thing mentioned. To count all the edge weights, add them up. This is going to be 3 plus 3, 1, 2. Add all those edge weights, it's going to be 10. Right? And if you ran the Dijkstra's shortest path algorithm on this, the same graph we ran in the previous class, we find the edge weight to be 12. So on the same graph, if I ran my Dijkstra's algorithm, same edge weights. Of course, in Dijkstra's, you start with the root, the starting vertex. So you start from this S, you get to this tree. If you count all those edge weights, it's going to be 7, 8, 11, 12. So what I want to say is the shortest path tree is not the same as the minimum spanning tree. Okay? So the minimum spanning tree basically connects all the vertices such that the sum of the edge weights is minimum. So you want to minimize the total weight of the tree connecting all the vertices. Whereas the shortest path tree, you want to minimize the distance from the source to every vertex. Right? So you can notice, if it was Dijkstra's, the other tree, from S to U, they would have been directly connected because this is of weight 4. Whereas you can notice in the minimum spanning tree, if you want to reach from S to U, this edge is not part of the tree. You have to go through like this to reach U. So you cannot guarantee shortest paths or minimum weight paths in a spanning tree, a minimum spanning tree. Okay? So if you want to find shortest path, you go for Dijkstra's algorithm. If you want to find a minimum weight tree that connects all the vertices, then you have to go for a minimum spanning tree. Okay, so you have to understand the difference between the two. Is that clear? Okay, so now coming to the time complexity analysis. Have you heard of this data structure called disjoint set data structure? Okay, so
Disjoint set.
So it's a data structure used to keep track of vertices in different sets. Okay, and you can find, so you can have vertices say A, B, C, D, and then E, M. So they are different sets. That is disjoint, so it means no vertex is in more than one set. And if you want to then merge two sets, then you one set, and each set has a leader, means a kind of like this component ID. The reason why we're using this data structure is, to start with, each of the n vertices, the vertices that we have in the graph are going to be their own set, which means A will be in its own set, B in its own set, C in its own set, and so on. Then when you merge the components, you're going to merge the two sets and make them as one set. So when you merge A and B is going to be in one component. And then C is in one, the rest are in their own sets. And then if you merge, again add one more edge, say C and D, or bringing them together, then they are going to be in one set. See? And then eventually all those sets will be merged, and you want to have only one set, because eventually you want only one component. Right? Is that clear? Now, so there are certain ways to merge things, which we are not going to see because that will take some more time. I should have seen in the other class. So the purpose is, so given a set, like for example you have something like this, and so if you want to find which set a particular element is, say if you want to find which set E is, you have to do it very efficiently. Okay? So if you have, say, B vertices, if all these things are B vertices, the time it takes to find which set has, in which set this particular element is going to take theta of log V time. Okay, so just assume that this is the time it takes to locate the set in which a particular element is. Okay? And then the merging process also takes theta of log V time. Okay? So it's also called union. So if you want to bring together two different sets, it's going to take theta of log V time. So why we need those two operations, find and merge? Because if you want to find which component this vertex D is, you have to know, because now A, B and F are in one component or in one set. So you want to find out which component it is, it's component A. So as I said, each set will have a kind of a leader to identify that set. So in our case, the leader is going to be component ID. Okay? So to find, given an edge, A, B or any edge, you want to find the component IDs of the two n vertices. You have to use a find operation to find what is the component ID of the two n vertices. That's going to take theta of log V time. And then when we merge things, we have to change the component IDs, right? So that will take again theta of log V time. Okay? So if you look at the pseudo code, to start with, each vertex is its own component, so you have to just initialize all the components. So that takes state of V time, because each one takes constant time. So you have V such vertices, so that takes state of V time. And as I said before, the first step before you run the algorithm is to sort all the edge weights. So this is the most time-consuming step, because you know any sorting algorithm, you want to sort n elements, how long it takes? N log n. These are interview questions. If you go to the interview, they'll ask this question. The best comparison-based algorithms, all your merge sort, quick sort, anything. You cannot do better than n log n. Okay? So here we have E edges. So if you want to sort all those edge weights, it's going to take theta of E log E time. Okay? So you sort that, and then we have to go through all the sorted edges. And that's what we did. We picked an edge and checked its two n components. If you have the same component or not, If they are not in the same component, then you can merge them, right? So to check whether they are the same component or not, as I said, it takes log v time. And then if you can merge them, then you can relabel all the vertex component IDs. That's what we are doing here. So basically comparing the two component IDs. And if you're merging two things of component ID U and V, and there are some vertices with component ID U here, and there are some vertices with component ID V here. So after you bring these two components into one component by connecting the vertices here like this, then everything has to become what? The lower of the two labels, which is U. So we have to basically change one of the two components, for the vertices within one of the two components, to have this label U. The others, this component can have the same label U. So that's why we have an if statement here. If say this is one component has a lower ID compared to the other component, then the component that has a larger ID will have to go through the change. That's why we have an if else thing here. Okay? And as I said, so basically you're merging the two sets, and that takes care of log v time. And we have to understand how many times we do this, right? So if you look at the examples, they are going through iterations. In each iteration, you are picking an edge like this to connect the two components. So if you have V vertices, how many times you need to go through this? How many iterations we have? If you start with say 6 vertices, you go through, how many edges you bring together eventually? 5 edges, right? So in general, if you have V vertices, if you want to connect them on a spanning tree, you need V minus 1 edges. So if you want to have a tree for V vertices, we need V minus 1 edges. Exactly V minus 1. And nothing more, nothing less. Okay? So we need to do this merging operation V minus 1 times. So each time you merge, it takes care of log V time. So it is state of V log V, because it's V minus 1 can be written as state of V. So you do this state of V times, and each time you do it's log V, so it is V log V. So the overall complexity, you have to put everything together. It takes state of V times to initialize the component, then E log E to really sort all the edge weights, then V log V to merge the components. So now if you see here, this term is not that dominating because you have a V and then V log V. So between theta of V and V log V is more dominating. Right? So you can kind of skip or discard this term. So this is the complexity. And based on what we saw in the Dijkstra's algorithm class, if you remember, I even said what? You can say between E and V, E is more dominating because you need to have E is at least theta of V, right? Okay? So it could be theta of V squared depending on the graph. So this is for a tree, this is for what is called a complete graph. Complete graph means you have edges between any two vertices. Okay? So, which means between these two terms, V log V and E log E, I can even discard this term and say the whole thing is just E log E. Depending on whether it is this or this, you can have